In this video, we're continuing our discussion of curve fitting. And in particular, we're going to talk about the extension of linear regression. So in the previous section where we discussed linear regression, the model function y was linear in x. However, we can have a model y that is linear in the unknown coefficients, but nonlinear in x. So in a general sense, the model function y can be composed of m terms with the following form. So y is equal to a1 f1 of x plus a2 f2 of x plus a3 f3 of x up to am fm of x, or y of x is equal to the sum of aj fj of x. So it's a linear combination of these functions, but each of the functions themselves does not need to be linear in x. So note that the linear regression model can be viewed as a special case of this general form with only two functions. So f1 of x is equal to 1 and f2 of x is equal to x. Then our model has the form y of x is equal to a1 plus a2x. Another special case of this general form is polynomial regression, where the model has the functional form as shown here. So for example, a0 plus a1x plus a2x squared plus a3x cubed up to amx to the power m. So the regression procedure constitutes finding the coefficients aj that would yield the least sum of squared differences between the data and the model prediction. So given a set of data xi, yi, with I goes from 1 to n, and if S is the sum of the squared differences between the general linear regression model and the data, then S has the form shown here. So S is equal to the model prediction of the data minus the actual data squared and the sum of all of those over the data points. If we plug in the form of our model as the sum of aj fj of x, then the form of S is shown here. So to find the minimizers of S, the derivatives of S with respect to the coefficients aj can be equated to 0. So taking the derivatives of S with respect to an arbitrary coefficient ak and equating to 0 yields the general equation here. So partial S by partial ak is equal to the sum as I goes from 1 to n of 2 times the sum as j goes from 1 to m, aj fj of xi minus yi multiplied by fk xi. And we're going to set that equal to 0. So this gives us m equations in our m unknown coefficients. So we can set this up in matrix form as shown here. And so this matrix has all of these sums as the coefficients of our unknowns a1 through am. And then on the right hand side we put the sum of y times the f values. And you can see that this large matrix here is symmetric. So for example, this term here, sum of f1, f2 is the same as this term here, sum of f2, f1. And similarly up to the sum of f1, fm is the same as the sum of fm, f1. So this matrix here is symmetric. And it can be shown that the system of equations always has a unique solution when the functions fi of x are non-zero and distinct. Solving these equations yields the best fit to the data, i.e. the best coefficients ai that would minimize the sum of the squares of differences between the model and the data. And note that the coefficient of determination can be obtained in the same way as described for linear regression as we discussed in section 9.2. So let's look at an example. Consider the data shown here and a model of the form y is equal to a1 plus a2x plus a3 cosine pi x. And we want to find the coefficients a1, a2, and a3 that would give the best fit to this data. So here's just a plot of the data as well as the model. This is the same data that was used in example 9.1 in the previous section. So the model is a linear combination of three functions. f1 is equal to 1 f2 is equal to x, and f3 is equal to cosine pi x. To find the best coefficients for this system, the following linear system of equations needs to be solved. So you can see that we have in each of these elements the sum of, for example, f1 xi f times f1 xi up to the sum f3 xi times f3 xi. So we want to solve this for our unknowns a1, a2, and a3. So we can set this up using Excel. So here shows all of the quantities that we're interested in, and you can see kind of how each of these elements are built, as well as the sums, which end up in going into our matrix. So therefore, the linear system of equations is given as shown here. And you can see by going into this Excel table kind of how these, where these elements go into the matrix form equation. So solving the system gives these estimates for the unknown coefficients a1, a2, and a3. So the best fit model has the form shown here. So y of x is equal to 0.16369 plus 0.83929x plus 0.64583 cosine pi x. And we can also use Matlab to produce the same, to find our unknown coefficients, and I've posted a script on the website that performs this calculation, and this is the output. We can see that we get the same coefficients, and then this is how the model fits the data as shown here. So now we can calculate the coefficient of determination, and again we use the same definition that we did for the linear model in section 9.2. So we can set this up again using Excel with the quantities shown here and calculate our r squared. So r squared is equal to 1 minus 0.13095 divided by 22.71429. So again, this is our sum, our residual sum of the squares, and this is our total sum of the squares. So r is 1 minus that ratio, which in this case is 0.994235. So r squared is very close to 1, which indicates that it is a very good fit, as we saw from the plot of the data. So let's look at another example. So we're given some data here, and we want to find a cubic polynomial fit to this data. So a cubic polynomial has the form as shown here, so a0 plus a1x plus a2x squared plus a3x cubed. So to find the coefficients, we can write down our system of equations that must be solved as shown here. Again, we can use Excel to build this system of equations, or of course we could use Matlab as well. So the linear system of equations, once we go through and calculate all those sums, we can build this matrix form shown here. So solving this system gives us the expressions for our unknown coefficients a0, a1, a2, and a3. Which means our best model fit has the form as shown here. So a0 plus a1x plus a1 or a2x squared plus a3x cubed. So we can also use the trendline feature in Excel if we wanted to plot this data. So adding a cubic trendline to this equation, we get, or to these data points in the scatter plot, we get the equation shown here, as well as the coefficient of determination r squared shown here. And you can see the values of the coefficients there. So we can again calculate the coefficient of determination using Excel, as we can see here. And when we go through this calculation, we get the same as what was shown using the trendline feature using the scatter plot. We can also do this using Matlab. So the Matlab script on the website calculates all of these parameters, and you can see that the model parameters again agree with both the methods that we just showed, using the trendline feature in Excel, as well as using setting up our table in Excel, and our r squared value again agrees with the previous methods. You can also use the built-in function in Matlab called polyfit to evaluate those coefficients, and again, can see that we get the same result. And so polyfit just orders the coefficients in the opposite order as how I have ordered them here, but the actual values are the same. So A3 here is the first one, and then A2, A1, and A0.